All right. So these are the libraries we have to import. ExcelR from that PCA, and this matplotlib is for the visualization. So we are going to visualize these first two components. Right. So let us load the data set, and you can see here this is our the same university data set we have worked in the clustering, the concept. Right. So just get rid of the first column. I need only the numerical columns because we are going to apply the scaling on this data. Okay, so this is the slicing of the data frame. So I'm going to get only the first column, then get the values in the array format. So these are nothing but the same the data set, but in a different data structure format. So here we have 13, 10, 89, 22, like that we have. So here. So on this data set, we are going to apply the scaling, scale the university data set. And let us see that scaled version of the university data set. Yeah, so this is the scaled version of university data set, right? Then fit the transformation, that is nothing but apply the PCA on the data set. So you can see the PCA. So these are the transformed data set. That means the PCs. Right. Now let us see the variance, the information content for each of the PC. So this is the information content. First one is 76.8% of the variance is being explained by the first PC, the second PC, third PC, like that you can see this. This is a cumulative, the first PC and first two PCs, first three PCs. So like that, if you consider all six PCs, we would get 100% information. And PC components, these are the PCA components. These are nothing but eigenvectors. Right. So here, okay, the core practice. So here I've applied scale transformation. This is as good as yes. So Z transformation, where you have the values mostly from -3 to +3. Yes. Right. So let us plot these first two pieces. These are the information. Okay. And the first two pieces, these are PC1 and PC2. Now let us plot these two pieces. Right. So this is a PC1 and PC2. Let us mark these data points belongs to which universities. So you can see the first row is for Brown University, Caltech, CMU, like this. Then let us plot it using the Seaborn. Right. So these are legend and these are the data points which belongs to the universities. From this, we can identify which are the universities are together, which universities are very far. So that's how we can find out the patterns from the data set. Okay. So one more usefulness of this PCA. So yesterday we did not discuss about this. We discussed about the multiple linear regression equation, right? And also we discussed a problem called multicollinearity. So when do we get multicollinearity problem in input size? When do we have multicollinearity problem in the regression equation? Yeah, one hint, it is related to correlation with the input variables. Okay, so proportional. So high variance among the variables, high variance. Okay. Right. If at all, if you have high correlation between the variables. So recall the example that we discussed as part of multiple linear regression. The example that we discussed is weight versus volume. Okay, weight versus volume. So the correlation between these two the variables is positive one, right? So then we discussed about, so these two variables are involved in the multi-collinearity problem. Then we thought of removing one of these variables, and we got rid of one of the variables using R square value and AAC values. Okay, so that was the procedure we have followed. Now, if you see, I have a data set. When I apply PCA on this data set, I would get PCs. Okay, PC1, PC2, PC3, so and so. How many number of input variables are there? Those many number of PCs I'll get. If you find the correlation between PC1 and PC2, what is the correlation between PC1 and PC2? So what is the correlation value between PC1 and PC2? For that matter, any PC, any pairs of PC? Zero. Exactly. So because if you see how these pieces are getting constructed, those are orthogonal to each other, right? Yesterday we have seen the pieces are constructed orthogonal to each other. That means the correlation between any pairs of PC definitely would be zero. That means if you use the species in a regression equation, you would never encounter the problem of multicollinearity. Multicollinearity. Because if you have correlation, high correlation between the two variables, then we'll run into an issue called multicollinearity, right? So if you don't have correlation at all, so there is no question of multicollinearity problem. That means whatever the output that you get, okay, so from the PCA, so I can use that output to build the regression equation. See, if you see here, right, so these are the two pieces. Let me increase here the number of pieces to 6. Let me go for 4. Yeah. So if you see here, PC1, PC2, PC3, and 4. Now what we can do is I can use these first 4 pieces. So these first 4 pieces are giving us 97% of the information. Then simply I can build a regression equation like this. Okay. Y is equal to beta naught, okay, plus beta 1 PC1. This is PC1. You can think of each one is a column. This PC2, PC3, and PC4 plus beta 2 PC2 plus beta 3 PC3 plus beta 4 PC4. So this is a regression equation I can build. So in this regression equation, we would never encounter the problem of multicollinearity, right? Because so the PC1 is orthogonal to PC2, so which is orthogonal to PC3, and if you take any pairs of the two pieces which are orthogonal to each other. So this another way we can build the regression equation. So which is often will get good accuracy instead of going for the normal variables or raw variable that we have collected. Okay, and this is one of the feature engineering techniques that we are going to discuss. All right. Now, so there is one downside for this approach. Yes, of course, we can use this and we can use this for the prediction purpose as well. But one downside for this approach is you cannot say what is, you cannot interpret what is this PC1 all about. Okay. So in case of our original variables, we had like this volume. Okay. Then we have weight, top speed, and horsepower. Right? So these are the variables where you can interpret what you mean by volume means. You can say there is a definition for that. It's a cab space. Weight is basically the car weight, top speed, HP. You can clearly interpret these variables. But when you say PC1, you cannot interpret what do you mean by PC1. At high level, based on the eigenvectors, you can identify whether the PC1 is influenced by which of the variables. But so if you want to if you want to interpret, so one-to-one basis, that is not possible. So that is one drawback for the PCA. if you want to really build a regression equation or a model using this PCA. But there are certain situations wherein the customers are not interested much about the interpretation of the model, but they are bothered about the model accuracy. Okay, model accuracy. So in this case, yes, so you can go for this, and you can you definitely will get a good accuracy when you go for this kind of model building methodology, right? Okay, so that is about the PCA. So now we are going to discuss about a supervised machine learning concepts. Okay. Yeah. So far, we have been discussing about the unsupervised machine learning concepts. Okay. So now we are going to discuss about the supervised machine learning. So what is the difference between this unsupervised and supervised machine learning? Right. So let us spend some time on that, and let us understand the difference between these two concepts. Uh, Unsupervised ML and supervised ML. So if you recall, the concepts, the techniques that we have discussed under this unsupervised machine learning algorithms are clustering, so association rules, PCA, and recommendation engine. So these are the techniques or the concepts that we have discussed as part of this. And coming to supervised, let me give you a few examples. We have discussed about the linear regression, all right? So we have discussed the logistic regression. Now, just recall the examples are the data sets that we have considered for for these concepts. The clustering, we have discussed about the university data set. Okay, university data set has certain columns. And for association rules, we discussed about the Titanic data set. PCA, again, we have used the university data set. Recommendation engine, we have used the movies, okay, movie ratings or something. Now coming to this data sets, the examples that we discussed about here is newspaper data. Okay, newspaper data, where we had two columns. One is the daily, the other one is Sunday. And also we discussed about the MPG, miles per gallon, with other variables. Last regression, we discussed about whether a customer would go through attorney or not. Right? Now, these are the data sets we have discussed. Now, one very important the observation here is when we were discussing about this linear regression, logistic regression, we clearly said that so which are all the variables are independent variables and which variable is dependent variable. So in this car example, this is my dependent variable. In this daily Sunday, this Sunday is a dependent variable and this is independent variable. So like that, we had a clear cut demarcation between the dependent variable and independent variables, right? When it comes to these data sets, so did we discuss about anything like independent variables or dependent variables? No. So we did not have that kind of a concept at all, first of all. So whatever the variable that we had, just we discussed those variables and meanings of those variables, and we went ahead and applied these methods. Meaning, so wherever you do not have any concept of independent variables, okay, and dependent variables, so if this concept is not there, then that problem so is basically unsupervised machine learning problem. And so we can apply clustering, association rules, or PCA, recommendation, and many more techniques are available. And when you have a clear cut objective that hey, this is my y variable, okay, this is my dependent variable, and these are all my independent variables. So if you have that kind of demarcation, then that is called as supervised machine learning algorithms. Right now, so we have already discussed a few techniques under supervised machine learning, and we completed this unsupervised. Again, we are going to discuss more advanced supervised machine learning algorithms. We are going to discuss. Yeah. So I hope that clarifies the difference between the unsupervised and supervised machine learning techniques. Right. So understanding business problem. So I guess we have discussed so this, right. So in one of the first few sessions, the flow of the data science projects. Can someone please confirm? Have we discussed this? Great. Yeah. Yeah. So we have discussed this. Let me uh, again touch this slide at a high level. Yeah. This is a flow of the data science project. Okay. So what are the different phases would be there in a data science project? So these are the phases. We have data. So using this data, we'll have to generate insights. Then once we generated the insights, we'll go for the features, then build the models, then predictions. So using the model, we are going to make the predictions, and based on the predictions, we are going to take the decisions. And there is a feedback loop here. So this feedback loop is to improve the model robustness. Okay, so that's what actually we discussed in the one of the sessions. Right. Now we are going to discuss about each of these activities. So what is data and what are the insights and all those things. We are going to focus on each and every activity, and we are going to understand what needs to be done in each of these phases in a data science project. Right. If you talk about the tools landscape, the data would be resides in database, be it SQL or no SQL. Okay. So the data has to be pulled into the environment of R, Python, or Tableau. So with these tools or programming languages, we can generate the insights. When I say insights, so understand the data. So that is what the insights means. Then the features would be generated uh, based on the data mining techniques and also based on the domain knowledge. Again, here we can use R or Python to implement the data mining techniques. Then we'll go for the models, model building, then prediction. So this can be done in using these tools, uh, or Python or PySpark cloud platforms. So finally, we'll get the predictions. And if you see the common tools here, yeah, R or Python. So mostly Python is a preferable language for implementation the data science project. Okay. Right. So, a question: what is the difference between? Yeah. So, what's the difference between insights, okay, and a prediction? Yeah. So that's right answer. What has happened? Insights is basically based on the data set. What are the data that we have here? Right? So we would apply the descriptive statistics like mean, median, mode, or visualization techniques and different uh, the slice and dice of the data in order to understand so what is happening or what has happened. So that is insights. The predictions means what is going to happen given a data set or given a data point. I have a data point, new data point. So for this data point, what is going to happen? That means we are going to predict. Let us say in a banking scenario, a new person has applied for a loan, for example. Okay. So I want to predict whether this person would become a defaulter or not. That means we are going to predict what is going to happen so in future. So that is defaulter or not a defaulter. So this we can identify using the predictions. Okay. And these insights are what is happening or what has happened in the past. Using the data set, you are going to understand that. That is the difference between insights and predictions. All right. Now we are going to focus on each and every part of this flow. The first one is data and insights. So if you see here the heading, dating the data. Okay, what do you mean by dating the data? Yeah. See, when you're in date with a partner, okay, what's the objective of dating actually? In general, phenomena, general sense. So, what is the objective of dating? When someone is in date with a partners, what is the objective? Any inputs? Understanding, exactly. Get to know them better. So, how the partner is behaving in a different situation. Okay, so is he or is her? So she is getting worried for small things, or how they are behaving in various circumstances, and all these things. So they'll spend a lot of time together, and they'll get to know each other. So that is the objective of dating. Right now, what do you mean by dating with the data? Dating the data. The same concept applies here also. Spend time with the data. Try to understand the data. What are the different patterns are available? What are the contrast are there? What are the similarities are there? Okay. What is the data are trying to tell us? So that is what actually dating the data, because data comes with lot of problems. If you see data nuances, if when you collect the data from the field, you would get a lot of problems. The data comes with a lot of problems unless you don't spend good amount of time with the data. And with the half cooked data, if you go for the model building, the model will also be half cooked, okay, half baked. So that means you have to spend good amount of time. So as we discussed, with the data and insights, 60 to 75% of the time you have to spend with the data. It's a huge amount. 60% to 75% of the effort you are going to spend with the data means huge amount of effort you are going to spend with the data, because the data comes with these problems. Feature noise. What is a feature? So henceforth, when you hear the feature, right, the column, the individual column is called as a feature, right? The variable one, okay, variable two, variable three, variable four. So these are called as variables, features, parameters, independent variables, attributes, regressors, right? These are the different names are there for the variables, and each one you can call as a feature. That means when you collect the data, we will have feature noise. When you say noise, what do you mean by feature noise? Value may not be accurate. The data that you collect as part of this, so this data may not be accurate because there are multiple reasons. So when you're collecting the data from the manufacturing or automotive domains, the sensor will use a lot of sensors to collect that data, right? Sensors may not be right, may not be working properly, malfunctioned. Sensor is biased. The calibration, so when we buy a new sensor, the manufacturer will give us the calibration information. Here this sensor might generate plus or minus, so 0.0005% or the value is error. Okay? But over a period of time, it will not be plus or minus, it is always plus only. That means every time it is generating the error to the positive side. That is, the sensor is biased. Okay? And sensor resolution. So you want to collect the data with high frequency. Let's say, for example, I have decided to collect the data for every second one data point, temperature. Let us say I want to collect the data of temperature, so of a manufacturing plant, or let's say, for example, a boiler. Okay, inside a boiler, there will be the temperature would be very high, right? So I want to collect the data inside a boiler for every second. So first second, let's say, for example, so 700 degrees. Second, okay, so 800. So like that, I want to collect the data at every second. This is temperature. So because of some problem that has surfaced in the sensors, the resolution has come down. So if you see, we are collecting data for every second. In a minute, how many data points will be there? In a minute, we'll have 60 data points, okay, per minute. Per minute. Okay. But so because of some issue has happened, now the sensor is collecting the data for every 2 seconds. First second, third second, fifth second, like that. For every 2 seconds, the data is being collected. That means the resolution has come down. So now in this case, the second case, how many data points would be there in a minute? We'll have 30 data points. Okay. The resolution has come down, the frequency has come down, right? So this is sensor resolution. Okay. Okay. Right. So call center nodes, transcription errors, data entry errors, right? And comments, tweets, blogs. When you collect the data from these sources, lot of issues comes. Okay, lot of problems that you'll have to solve. Okay. Now, data, yeah, missing features. We'll have the missing data. When you collect the data, for example, age details of a customer. Okay, so here we have a 50, okay, 45. So this value is missed. So then we have 35, okay, 30. So like this, the data is there. So here the data is missed. So this also we have to analyze and we have to identify what is the best method to deal with this missing data. Some features values might be missing because of communication or storage failure or human error or sensors went down. Okay, and then we have non-normal feature distributions. So majority of the times, so we would get the exponential distributions as well as log normal distributions are more common rather than normal distributions. Okay. So for this kind of thing, what we can do is we can go for the log. So that so to some extent we can reduce the effect of these distributions, and we can approximately convert these distributions into normal distributions. Heterogeneous features. So when you say heterogeneous features, the ranges, scales, distributions are different kinds of. For example, if you see, if you have a data set that comprises of these features, let's say age, income, temperature, RBC counts, right? So age is in tens, income would be in thousands of lakhs. So temperature again is in tens or hundreds. RBC counts definitely would mean millions, right? So the scales are different scales, the distributions are different. So this data is called as heterogeneous data. So this also has to be treated appropriately. So as we discussed in one of the techniques, clustering. In the clustering, we have seen that the expenses, the scale of the expenses of the college is very high. So that is in thousands, and all other features are in hundreds or tens. Then the expenses is dominating the entire analysis. So what we have done, so just we have applied the scaling, on the data set. So that's how actually we have solved the problem. So here also when you are building the algorithms, you have to take care of these things. So when I say spend the time with the data, identify any of these issues are there in the data set. Find out, do we have any feature noise? Find out, do we have any missing feature? So find out what are the distributions of this data. So find and apply the normalization on the data set, multimodality features, right? And also go for, excuse me. Yeah. So go for the descriptive statistics. Understand your data set, compute the descriptive statistics for all the columns like mean, median, mode, and go for the visualizations, histograms, bar chart, okay, heat maps, and whatever the meaningful chart that you can apply on this data set. Go and apply the data on these data sets and understand the data. What do you mean by understanding the data set? Let's say, for example, so if you see here, so in this Zoom session, we have 110 people have joined, and we can collect the data. I can roll out a simple Google form. So how you are filling the attendance, right? Similar to that, I can roll out one more Google form to collect the data like this. For example, the name, college, branch, date of birth, okay? So your location and your academic performance. So this data I can collect. Now, what do you mean by understanding the data? So understand data means how many number of people are joining from different branches. Okay, from IT, how many? CSC, okay, mechanical, so electronics, electrical, and a civil. So I can understand, and different any other the graduates. So BSc, okay, BCom or degree, right? So these kinds of the branches are the other bachelor degree. I can understand, I can count. So this gives me some idea about the audience. Date of birth. From this date of birth, I can compute the age. Yeah, how many of them are? So more than, let's say, 20 and less than 22, and more than 22. So this age category I can understand. Then the location. So most of them are joining from which location, and academic performance. Okay. So then I can also understand most of the IT. So IT branch students are from which location? So are they from Chennai? Are they from Bangalore or Hyderabad or different locations? And also the academic performance. Most of the students who have achieved more than 90% of the marks are from which location and which age group and which branch. Okay, and less than, let us say for example, so more than 80% and less than 90%, again go through that. So these are the insights we can generate, so from the data, that gives me additional information about the data set. So when you generate these things, right, so that gives you more understanding about the behavior of the data set, and by doing so you will be able to understand whether this column is important for me or not, whether this feature is also important for me or not. So this kind of the idea you would get when you slice and dice of the data, and when you try to uh, go for the visualizations or go for the descriptive statistics. So if you want to do all these things, it takes a lot of time, because the data, first of all, when you pull the data from the databases, so these problems will be there. Then you have to process the data, you have to clean the data. Once you clean the data, after that you will go for this kind of uh, the visualization techniques or descriptive statistics. That also takes a lot of time. Okay. After that, then you can go for the feature engineering. So that's where the time would be spent on these activities. All right, so not normal distributions. When you see the histogram, so of a feature from the data set, this is basically a histogram, the distribution of a feature. So what kind of distribution is this? Do we have a skewness in this, or it is perfectly normal distribution? It's a skewed distribution, right? Yeah, positive skew distribution that you can see here, like this. Okay. Now, so when you use this feature as it is, the algorithm would not be able to understand the patterns from this feature. So what we can do is I can apply log. Okay. So log to this feature. When I apply log to this feature, I'll get this. So this is a bell-shaped curve, okay, approximately normally distributed. So this feature is very easy to use, and from this feature, the algorithm would be able to understand the patterns from this feature. Okay, and one more here. So this is another feature distribution here. So this hopeless actually, right? So completely skewed, highly skewed. So a lot of all the values, almost all the values, so have been concentrated or focused or lies in this range. Excuse me, in this range, and there are very few values in this range and in this range. So when you use this, model completely ignores the other these values, these categories, because a lot of values are happening or so occurred in this range. Okay, so this is a problem. So when you have highly skewed data, what we can do is apply logarithmic transformation on this feature, then I will get this. I would not say this is approximately normal distributed, but this feature is a way better than this feature. Then I can ignore this feature, I can go with this feature. Okay. So that means you have to identify the distribution of each and every feature and check whether we can convert that into a near approximately normal distributed feature by applying logarithmic transformation or by any other transformation that you can go for. Okay, so if you're not sure about what kind of transformation can be applied, so the best method is a more generic transformation technique is Box-Cox transformation. Okay, so Box-Cox transformation you can apply, and you will get to know that the lambda value, based on that you can transform. Right, so that is about the data. The problems comes with the data set. Now coming to the feature engineering. So remember our workflow, we have the data, okay, then insight or EDA. Okay. This phase, okay, this activity, so often referred as EDA, exploratory data analysis or insight phase. So after that, we'll go for feature engineering. What is the feature engineering? The feature engineering is out of all the features that we have collected, okay, as part of our data. So when you're collecting data here, you would collect a lot of features, right? So these are feature one, feature two, okay, feature three. You would collect a lot of features like this. But are you sure that all these features are important to us? We do not know. So at the time of problem statement, at the time of data collection, we would have collected a lot of features. We thought that, okay, so these features might be so interested to understand, and these features might be resolve the problem of so whatever we are trying to address. Okay, so this is a phase where we'll take out each and every feature, and this feature is useful for us or not. So each and every feature we'll take out, we'll understand the importance of the feature in addressing the problem. Okay, so that is the feature engineering. And also, that is first step, identify the important and significant features from the data set. The second part is fabricate new features. Fabricate new features. What does that mean? So by making use of existing features, so these features we are going to compute the new features. So how are we going to compute the new features? By F2. So by making use of these features, I'm going to compute new features by taking the ratio or by applying some the arithmetic the operations F2 plus F3 or F3 plus F4. So like that, we are going to have this new feature. This is more meaningful than having F2 and F3 alone in the data set. Right? So that is called as feature fabrication or constructing new feature by making use of the existing feature in the data set. Right. So let us understand with one example what is this feature engineering and how we can construct the new feature by making use of the existing features. Yeah. So this is where we are now. Right. Then we'll discuss about this and the other aspects as well. So an example. So example here is, so we want to build a model, a machine learning algorithm. So that predicts a physical card transaction that has been done is a fraudulent transaction, or it's a legitimate transaction, or it's a genuine transaction. So that is what the problem that we have. So for this purpose, okay, we have collected these four features. The features are the time and place of current transaction, and time of place of previous transactions. Right? These are the four features we have collected. And based on these four features, we are going to build the model. And let me give you the intuitive understanding of how we are going to use these four features to address this problem. What is the problem statement here? So there is a physical card transaction that has happened, debit card or credit card, and we want to find out whether the transaction that has happened is a fraud transaction, unauthorized transaction, or it's a genuine, it's authorized transaction. Yeah, the bank wanted to understand what the risk associated with a single transaction. So that is what we want to find out. Now, so let us say, for example, the current transaction, so that has been done in Bangalore. Okay, Bangalore. So let me first give you the information on the previous transaction. The previous transaction that has been done in Chennai. Okay, so sorry, Chennai. So at 5:40 or 5:30 p.m. today, the current transaction that has been done, so at 5:45 p.m. today. Now, based on this information, so can you tell me, so whether this transaction is a genuine transaction or it's a fraud transaction? So can you post your response? What can you say about this transaction? Right, it's a fraud, so that we can easily identify and understand, because So no one can travel. Okay. So within 15 minutes from Bangalore to Chennai, even if they use the advanced mode of transportation, still that is not possible, right? So that is the key idea intuition we are going to use here. So using these four features, what we are going to do, we are going to construct new features. The new features are like this. The first feature, the derived feature one, we are going to compute the distance between the previous transaction and current transaction. Okay, the distance, the place, the distance between these two places. Then the time lag. What is the time difference between these two transactions? Right? So this is derived feature one. Then we are going to use these derived features in derived feature two. That is velocity. Velocity of this transaction. That means, so how fast so one can travel, or what is the velocity between these two transactions? How do you compute the transactions or the velocity? This distance by time lag, that gives me the velocity from previous transaction to current transaction. Now this velocity we would compare the most advanced the modes of transportation velocity. Let us say the most advanced the ways of transportation velocity is, for example, 500 kilometers per hour, okay, per hour, and this is our most advanced the mode of transportation. Let's say, for example, that means 500 is a velocity. We will compare our transaction velocity with this reference value. Okay, our velocity, let's say, for example, so 1000, okay, kilometer per hour. So my velocity, transaction velocity is 1000 kilometer, and wherein the most advanced the mode of transportation velocity is 500 kilometer. Then this is more than, okay, more than uh, the velocity basically, right? The 1000 kilometers or the transaction velocity is more than the reference velocity. Then we can simply say that, hey, this transaction is a fraud transaction. If at all our transaction velocity is, let's say, 100 or 200, 300, so then we can say, so probably in this way, so this is not a fraudulent transaction, probably we have to apply some other methodologies. Okay, we can say in this case, so this is not a fraudulent transaction, and we can reroute it to some other teams so that they can check some other aspects of the risk associated with this transaction. So like that, so whatever the raw features that we have, so how we can construct the derived features, the feature fabrication and derived feature two, and ultimately I'm going to use this velocity to find out whether the transaction is a fraud transaction or not. And I don't need these features to be used in the model. Okay, I'm going to use this only one feature I'm going to use, and these features are not needed. But to compute this, yes, of course, we need this in the raw data form. So once I compute this velocity, okay, so I don't need these features at all, and I can directly use this one feature instead of these four features in the model. So that's how we can fabricate new features based on the given inputs. Right. Okay. Now we are going to discuss about models. Yeah, this is where actually we are going to spend a lot of time. We are going to discuss bunch of algorithms as part of these models. We started a discussion about with the data and insights, and we discussed a few aspects of the features. Then we're going to discuss about the models. And someone has asked a question: what are the different techniques that are there in the feature engineering? We have PCA. PCA is one of the feature engineering techniques. The second one is we are going to discuss about decision trees, tree-based methods. Yes, so tree-based methods we are going to discuss as part of this model, and this can be used as a feature engineering techniques. Okay. Third one is we have something called as RFE, recursive feature elimination. So we have methodology called select k-based method, select k-based select k-based methods. Yeah, these are the different feature engineering techniques we can use to identify, and out of which we have discussed this, and we are going to discuss about this also. Yeah, you can explore this recursive feature elimination and select k-based method. Okay, models. Now let us discuss about These algorithms, models means algorithms. Okay. So before that, the model building or algorithm building. So when you are building an algorithm, and this is my data set. Let's say, for example, we have rows and columns. It is 100% data set. So before building the model, what you do is we would divide the data into three portions. So one is testing data. Okay. The other one is validation data. And this is training set. So training data, right? And so what are these three parts are meant for? The first one so is to build the model. When I say build the model, recall how we have built our linear regression equation. What do you mean by building the linear regression? Building the linear regression is nothing but identifying beta naught values and beta 1 and beta 2 values. So when you have these values, that is what actually building the model means. So that is what, that's how actually we can say, when you say I'm building a model, the parameters have to be identified, or the model would understand the patterns from the data. So that activity, so for that activity, we have to have a data set. The data set is called as training data. We are going to train the model based on this data. The model would understand the patterns from the data set. So further, we'll use training data set. Then the validation would be used to fine tune the model. Okay, once you build the model, so you may not give any guarantee that you will get the state of the art model, the best model. Right? So the model has to be improved. So that improvement would be done using this validation data set. So once you feel that, hey, my model is the best model, okay, and no one can come up with the best model than this. So once you feel that is the best model, then I would apply testing data set to the model. Then I get the accuracy. So accuracy, this accuracy, so would be so reported as part of model documentation. Hey, this is accuracy that I have got on the testing data set, and this is a final accuracy there. And also you can expect this kind of similar kind of accuracy when you go for the real the predictions using the field data. So these are the three parts of the data that we have to divide when you are going for the model building. And what is the proportion actually? So the training data would be around 70 to 80%. And this one is around 10 to 15%, and is also around 10 to 15%. This is a proportion where you can divide the data set. Okay? And very often, so we'll not have actually these three portions, three parts. We'll combine these two. So training and validation will combine, and we'll have so testing and training data. And so here also we'll have 70% is into training and 30% into testing. Yeah. So ideally we should do this, but so practically, so mostly we are going to supply like this. So we'll divide the data into training and testing and 70 and 30%. Okay. Now we are going to discuss about two kinds of the machine learning algorithms. Okay. So one is a regression task. The other one is classification task. So classification task, what are these? Simple example is regression task is linear regression. Classification task is logistic regression. Now, so by this time you should be able to understand, so what are these tasks all about? Logistic regression. So in your y variable, so if you have a numerical data, then that is called as regression task. In your y variable, so if you have a categorical data, you're like yes or no, then that is called as classification task. Categories, then that is called as classification task. For regression task, are we going to apply every time only the linear regression, or do we have any other different methods? We have much more sophisticated methods to solve this regression task. When I say regression task, in your y variable, if you have a numerical data, numerical values, then that is called as regression task. And we can solve that problem using the regression kind of algorithms. Not only linear regression, we have many other regression based methods are available. When it's regression based, so those methods can be used to solve the regression tasks. What are the other examples? I can use support vector machines. I can use random forest. I can use neural network. Okay, and we have cart. So we have xgbm. These are the different models actually. LGBM, so and so. There are many other models are available. So I can use all these models to solve this regression task where we have y variable is a numerical variable. And coming to classification, the classification models, yeah, as we discussed, if you have the categorical variable in the y dependent variable, then I can call that as a classification task. Okay. So do we have only a logistic regression to solve that problem? No. Again, we have many models or many algorithms that are there. So for this classification task, so we have a decision tree based method called C5.0. I can use neural network, and same the lgbm xgbm and all these things. So these are examples that we can use, algorithms that we can use to solve this classification task, right? So regression problem is pretty straightforward. And basically the parameters would be learned. So in case of the y variable is the numerical variable, and how this regression equation that we have built, right, it's a straightforward. Okay. And when it comes to the classification, so we have to understand so how this classification would be done. Okay. And we'll spend good amount of time on this classification, and we'll move to the regression tasks. So first we are going to discuss about classification task. All right. So let us take a break now, a 5 minutes break. Now it is 6. Okay. Yeah. So we'll resume our discussion at 6:05. Okay. All right, so let us continue our discussion. Right, now coming to the classification. Let us understand what do you mean by classification? What's the definition of the classification? The formal definition of classification is this. So partition the feature space into pure regions assigned to each class. Right? Some words are there, some jargon. Uh, there are a few terms which we need to understand. The classification is all about partition, some space. What is the space? The feature space we have to partition into something like a pure regions assigned to each class. All right. So let us take an example. Let us try to understand what is this definition mean, and we'll come back to this definition after that. Let us see whether these sentences, what is the sentence that we have here, make sense to us or not. Let me uh, okay, populate some dummy data here. The data is related to banking industry, customers age, customer salary. Okay. Yeah. So this customer, okay, is a defaulter or not. That is my class variable or dependent variable. Dependent variable is also called as a class variable, a label. Okay. And the first customer age is, let's say, for example, 22 years. The salary is, okay, 50K, 25 years. Okay, 50K. And the class variable is defaulter. Then we have 45 years, 200K. Okay, not a defaulter. Then we have 30, okay, 30 years and 65K defaulter. Okay, 50 years, 250K, not a defaulter. So I hope you know what is a defaulter, not a defaulter. Okay. A person who has availed the loan or credit card from the banks, they don't pay all the EMIs, then the banks would term them as defaulter. Okay. Not a defaulter means, so all the EMIs have been paid promptly and completely. So that is that customer is not a defaulter customer. So that is the demarcation. Now the banks wanted to understand the risk associated with each of the account holder, the loan, the credit cards or the loans. Okay, so if at all that customer would become a defaulter, then that is a high risk for the banks, because the banks are going to lose the money. Right? So that is what actually the banks wanted to understand. So what are the customers are risky customers and who are the customers are loyal customers. Right? So this is my data set, for example. Now let me mark these, or let me have a scatter plot for this two uh, features. This is my feature one, feature two. Okay. So feature one, that is nothing but I'll say this is age, for example, and this is salary. Feature two. Let me mark this. Let's say, for example, this is 20, 25, 30, 35, okay, 40, 45, 50. And here we have 50K, 100, okay, 150K, 200, 250. All right. So we have seen actually a new term called feature space. Okay, feature space. What is feature space? We know what are the features. Features are nothing but these two are called as features. The space, the two-dimensional space, are based on number of features. The space created by the features is called as feature space. So this is the 2D space. When you have the two features, this space is called as feature space. Right? Right. Now let us mark these data points into this feature space. The first data point, 2550. So this is where actually I can mark the data point. So that is, what is the class label for this? D. That means defaulter. Okay. Then the other one 30, 65. 30 and 65 is somewhere around here, for example. So this is also defaulter. Okay. Now let us mark the other data points. Here we have 45 and 200. Okay. 45 is here and 200 is here. This is not a defaulter, not a risky customers. Right? And then 50, 250, and this is here somewhere. Let me put here. Not a defaulter. Now, what we have to do with this feature space? As per the definition, partition this feature space. Okay, so let us partition. That means divide this feature space. So divide this feature space. So how should we divide this feature space? We should divide this feature space such that the pure regions are created. Okay. Again, the new term called pure regions. What do you mean by pure regions? I have a region, let's say for example, in this region, I have data points that belongs to the same class or same label. When you say label or class, these are called as classes and labels. So default is one class and not a default is another class, right? So if you have a region, if that region comprises of the data points which belongs to the same class like default and default, then I can call this is a pure region. And also have a region, a space, if at all that has only not a defaulter data points. Okay. Then also I can call this as pure region. And then a region that is a mix of both classes, defaulter, not a default. In this case, I cannot call this as a pure region. These two regions are pure regions and this is not a pure region. Now, coming back to our classification definition, I have a feature space here. This feature space has to be divided. How we should divide this? Such that the pure regions are created assigned to each class. Now, can you tell me this region? So this is one region. We have divided this entire feature space into two regions, right? Into two regions. This is one region and this is another region. Now tell me, do we have pure regions in this? Do we have pure regions here? Yes, we have pure regions because so this region here we have only the data points that are belongs to defaults, defaulter, and here we have only the data point that belongs to not a defaulter, not a defaulter. That means so we are successfully created the pure regions, and this region, so how we can say this region we can assign to defaulter region because all the data points belongs to defaults only. Then I'll say that so this region I can assign to the class of defaulter and this region I can assign to the class of not a defaulter. Right. Now let us revisit the definition of the classification. The classification definition is classification definition is partition the feature space, the space created by these two features, just divide that feature space such that the pure regions are created assigned to each class. So that is the definition of the classification. Let me go back to the earlier slide and let me know whether that makes sense to you or not, the definition here. Just go through that and let me know if it makes sense to you or not. So this is the definition of the classification. Yeah, please post your answers yes or no. Great. Yeah. Right. Now, so this is what actually we're talking about the classification. So this is what the models would do when you say machine learning algorithms, ML algorithms, right? So this is what actually all the ML algorithms in the classification tasks they'll do. Okay. Now, how do we use this algorithm? Let's say, for example, we have built algorithm, machine learning algorithm. So this is what the machine learning algorithm is actually, right? In case of classification. Now I want to use this algorithm for a prediction purpose. Okay. So I have a new customer who applied for a loan. So that customer age is 29 years and the salary is around 63 years. Sorry, 63K US dollars. And I have to take a decision. So whether so for this person would become a defaulter or not a defaulter. If this person becomes defaulter, then I would not approve so his or her application. Otherwise, so I would approve the application or disburse the loan. That is what the idea here. Now I want to find out. So this person would become a defaulter or not a defaulter. So let us see how we can use this algorithm for this prediction purpose. Let us mark this data point in this feature space. So 29 years is somewhere here and 63 is here. Okay, so this is where the new data point falls under. So since the new data point falls under the defaulter region, what we do? So we will assign this defaulter class to this new data point. Then I'll say that, hey, this guy would become defaulter because so this data point is very near to the defaulted customers. That means whatever the behavior, so these guys has similar to that. So this new guy also will have the similar kind of behavior. And this data point falls under the default region. Definitely this guy also will become defaulter. And most of the times, when I say definitely, most of the time, that is what actually we have seen in the data as a pattern. Yeah. Then we'll say, hey, we'll not give you the credit card or loan for you for this customer. Then there is another customer, let us say, for example, 55 years. So the salary is, let's say, 260. So for this customer, so we have to take a decision whether this customer would become a defaulter or not. Now 55 years is somewhere around here and 263 is somewhere around here. Okay. Now, since this customer fall under the not a default region, then I'll say that, hey, this customer would not become a defaulter. So because the pattern, the behavior of the customers who has this kind of age and salary is this, then I would say, go ahead and issue the credit card for this or loan for this guy. So that's how we can predict for a new data point using this classification algorithm. All right. Now, so if you see here, the classification, again, the same thing, whatever we discussed. So here we have two classes. Okay. So these are class one and this is class two. So whenever you're reading material related to the machine learning or the deep learning, the classes would be denoted using the different symbols like asterisk or plus or different colors. So if you see a different colors like red and blue here, we should understand that these two are different colors. So you can say this is a defaulter and this is not a defaulter. Or some other classes, what are the classes? So this color differentiation is to give the difference between the classes, the class one and class two. Right? Now, these are the two features here we have. And this line, so this is a partition or dividing this feature space into two partitions. And this is called as decision boundary. Okay, so this line, whatever the line that we are using to divide this feature space is called as decision boundary. And this is a region one default region, and this is not a default region. And now a question for you all. So do we have pure regions here? Right. So there is no, yeah. So it's not the pure regions because you can see here there are certain data points which are misclassified. What are those? You can see here. This is one data point where we have misclassification, and this another data point, and this another data point. So this data point should have been so classified into this, but this is a misclassification. So this is went into other region, and this is also under misclassification. So because of these misclassifications, we cannot say we have 100% pure regions. But the based on the majority, okay, based on the majority, I can say that hey, this region is a default region, because mostly most of the data points belongs to this class, the default class, and there are a few, one or two data points that are coming from this non no defaulter class, and we are not going to give much importance to those data points. So we can term, or we can define this region as or this partition. So we can say this as a default region, and this is not a default region. Right. And so what are the data points so that have been misclassified? You see this data point, this and this data point. So this would contribute to the classification error, the classification error. So let's say, for example, I have a scenario like this. Uh, this is one class, positive class, and this is negative class. What are these are the data points. So the way we have discussed in the previous slide, right? So you can think of these are the defaulters and not a defaulters, or not a defaulters and defaulters. These are the partition. Now can you tell me what is the classification error for this kind of scenario? So how much is the classification error for this? No error, zero error, exactly, right? Because there is no misclassification. When I say misclassification, so this is plus 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 minus 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 plus. So if you have the region, this is one region and this is another region, and wherever you don't have any pure regions, that means mix of the data points from the both classes, then there would be some error. And here also some error is there. And where you have a clean and neat separation of the data points belongs to each classes, and there is no error at all. The algorithm accuracy for this is 100% accuracy of the algorithm. And here, yes, based on this, how many number of data points that have been misclassified, based on that, the classification error would be computed. So here you can see these data points are misclassified. What do you mean by misclassified? So there is one question so someone has posted, what if actually 60 years, what is that? 60 years or 50 years and 50 years of age and 60K salary. Okay, 60K salary. So this data point mostly would get misclassified. So it would come under, for example, so in this or in this. Okay? So this is one of such case. So we cannot do anything about this. So probably you can say this is an outlier or something like that. But so this would contribute to the classification error, because this would not be classified correctly. So that would fall under here or here. So that will mostly misclassify data point. And because of that, the classification error would be there. Okay. Right. So decision boundary for three class problem. So what do you mean by three class? First of all, I have a data set like this. So let us say this is my class. You can think of this is okay, feature one, okay, feature two, feature three, and this is my class variable. If you all in the class variable y variable, so if you have distinct number of categories, okay, let us say I have yes or no. So if you have only these two the distinct values yes no yes no yes no for all the data points, then this is called as two class problem. Two class problem. That means I have only two classes, S class or no class, or default class, not a default class. Patient has a cancer, patient did not have cancer. Right? So these are only two classes. That is called as two class problem, based on the number of distinct values in the class variable. Let us say I have one more category. This is on hold. I can also put a file on hold, the application on hold. That means how many categories we have now? Three categories. So this problem is called as three class problem. So how many number of distinct unique values are there in the class variable, and based on that we will refer that problem data set as those many number of classes. Okay. Now here we have three class problem. So how? Based on the color coding, you can see we have three different colors. So blue, okay, green and red. These are the three different colors, And that's why we can say this is a three class problem. Now tell me, do we have pure regions here? No. Yes, that's right. Okay. So if you see here, this is not a pure region because this mix of the data points from green, red, and blue. And this also mix of data points from green and red. But this is one region, this is a pure region. Because in this region, we have all the data points. So if you consider this region, we have all the data points that are comes from only one class. So that is a blue class, and that is nothing but setosa. Okay, so this is one of the classes. Actually, this is a flowers data set. I'll show you what is this data set all about. Right. So this is not a pure region, and this is also not a pure region, but this is a pure region. Now we have to assign the classes for these partitions. This is also classification, right? So this is my feature 1 and feature 2. We have partitioned this feature space such that the pure regions are created assigned to each class. But it is not possible every time to form the pure regions. Right? The classification objective is just to maximize the pure regions. If at all, if you're not able to create the pure regions, just maximize wherever it is possible to create as maximum as possible for the pure regions. Just go ahead and partition the feature space. And in this case, if you see here, this is completely pure region. And here, yes, we could not successful, but the majority of the cases in this region, the green data points. And I'll turn this the entire region as green class. And here we have red data points. I'll turn this as a red region. Okay? So that's how we will assign each partition to a class like this. Okay. Now, so let us talk about a simple decision boundary. So when you are creating the decision boundaries for a two class problem, we have two classes, right? So there's a class 1 and class 2. So there are various scenarios how we can divide, how we can partition this feature space. The first one is a simple decision boundary. What is a simple decision boundary that we can use to divide this space? It's a linear line I can use. It's a linear line so that I can have two portions or two partitions. These are class 1 and this is class 2. Do we have a pure regions here? Yeah, everyone. No, we don't have pure region here. So that's right. So you can see here, this is a data point which is misclassified. This also misclassified. These data points have been misclassified. So that is happening with a simple decision boundary or linear line. And there is certain amount of error. So because of this misclassification. Okay. Now let me give you the idea how we can improve the accuracy of the algorithm, the classifier here. When you say improve the accuracy of the algorithm means reduce the number of misclassified observations. That means this is one data point which is misclassified. What if actually if I send this data point to this region, then this data point would be correctly classified. And this also, if I send this data point to this region, then this data point also would be correctly classified. And this data point to this side, then this also correctly classified. That means if I reduce the number of misclassified observations, then I can improve the classification rate, the accuracy rate. Now let us see how we can do that. So instead of using this linear curve, why don't you use nonlinear? I can use like this. Now, if I use this nonlinear curve, so this curve, so would the accuracy be improved in comparison to linear curve or not? Let us say these are linear, these are 1 and these are 2. So what do you think? Which one we will have more accuracy, 1 or 2? Right? 2, exactly. So using this non-linear curve, so we can improve the accuracy like this. Okay. Now this is actually, we can see this is a medium decision boundary, medium complex decision boundary. Right. Now, so do we get here, if I use the nonlinear decision boundary, do we have pure regions here? Still no. Still we don't have the pure regions because there are certain data points here and here and here. These data points would contribute to the error. Can we increase the accuracy further? Let us see. Let us increase the non-linearity further. What happens? Let us see that. So this is what happens. Now tell me guys, careful, just observe this. Do we have pure regions here? Yes, everywhere we have pure regions. Exactly. Now the accuracy of this model is 100%. So accuracy is 100%. Right? Now, though this model accuracy is 100%, but this model is not going to be useful for us. This model we should not use. Right? So why? If you see here, so as we discussed, this region is basically a red region, and this region is green region. You can say this is yes and this is no. That means, so you can approve the credit card. So for the people who fall under this region, yes, and this you reject or no. Right? So there are certain data points that belongs to no, so that fall under in this region. So for this single data point, a local region has been found, and local region has been found for this and for this also, and for this also. Okay? Now, because of these local regions, the model would not give us the correct predictions. So how? Let us take an example here. So these are feature one. Let us say, for example, this again age, and this is salary. Okay. So let us take the same example. Okay, the age and salary, and I want to predict the class variable for this. So recall the data set that we have populated, the same data set. Let us say, for example, uh, I have the years of 24 years of age. The salary is, let's say, 55K. Okay? So ideally, so based on the previous patterns, so we should give this guy would defaulter or not a defaulter. Just recall the previous data set. So as per the previous pattern, so we have said that this guy would become defaulter, right? That is what actually we have discussed. Now let us see where this data point would fall under. So lower age and lower salary, this data point, let's say for example, fall in this region. This is the region, so the data point would fall under. Now what is this region? This region so is created for this data point, green data point. What is this green data point? Yes, go ahead and issue the credit card. That means, so this guy would not become a defaulter. This entire region is for those kind of people, not a defaulters, so that we can go ahead and issue the credit card. So this data point falls under in this region, then we will have to take the decision. This guy would not become a defaulter. Go ahead and issue the credit card. What happens? So we'll issue the credit card for this guy. This guy would use a credit card. He would become or she would become defaulter. The model is wrong prediction. One more example. So 50 years of the age and 200K salary. And based on these characteristics, so in the previous slides that we have discussed, this guy would not become a defaulter. Go ahead and issue the credit card for this guy. That is what the pattern that we can say. Now this data point, let us mark it. So here when we marked it, so this data point falls under in this region. So though the global region is yes, but the local region is no. Right? So that means this region is basically for the defaulters. This region is for the defaulters. Now the model would predict that this guy would become a defaulter. Then we would decline the credit card or the loan application for this customer. That means this is also a wrong prediction. That means, so if you try to increase the complexity, so like this, so if you want to force the model to get 100% accuracy, okay, 100% accuracy, then the model so would try to So eventually, so overfit the model, that means it tries to understand and remember each and every data point from the data set and forms the local regions in the global regions. When you have the local regions like this, so your model would definitely give you the wrong predictions. Always it gives you wrong predictions, and this model is not going to be useful for the productionization for the field predictions. So that means, so we should not go for this kind of overfitting models, and the best model that you can go for is this. So this is the best model that you can go for, right? Even the model, if the model is like this, okay, the model is linear or simple decision boundary. So this model is also not good because a lot of error is there. So you can see a lot of data points have been misclassified. And even if you go for this kind of model, so this model for sure, it is not going to be useful at all because the model is overfit. Okay. Yeah. All right, so we'll stop here for today. So we have to cover some more material related to machine learning concepts. Okay. And Monday we'll continue the machine learning concepts. Then we'll discuss our first model, that is a decision tree. So we'll see based on the, so how far we'll cover. Then we'll start our first model on the decision tree. Right. So questions: SVM is nonlinear model. Is it overfit? See, nonlinear models. Yeah, nonlinear models doesn't mean that they are overfit. So if you increase the non-linearity, then those models would overfit. Yeah. So SVM, yes, you can have linear or non-linear as well. Yeah. So we'll share the code and we will communicate. So what we'll do is actually we'll place all these codes and the data sets in the Google Drive, and we'll post the Google Drive link in the Telegram application so that you can access those things. So if you're not part of the Telegram, so please post your mobile numbers so that we can add you to the Telegram application. Karan and Tarun, please note down those phone numbers so that you can add it to the Telegram application. Yeah, so that's all for today. And so thanks for joining today, and we'll meet on Monday. Yeah, so great weekend, and we'll meet on Monday. Thank you, guys. Yeah, please post your mobile number so that we can add it to you to the Telegram application. Yeah, sure. Karan, can you please post that attendance link?
Yeah, sure.
Once again. Yeah. Okay, guys. Yeah. So if you have posted already, you can drop off. Okay, thank you. We are closing the